Good afternoon, everyone, and welcome to the College of Engineering Virtual Brown Bag Series. My name is Gautam Das. I'm the Associate Dean for Research, College of Engineering, and I'll be your host today. Before I introduce today's speaker, just wanted to let you know that this session is for 1 hour. We will get done with the presentation a little bit before that, and there'll be enough time for Q&A. And for asking questions, please look at the Q&A window on the Teams application, and you can type in your questions, and we will read them out as and when your turn comes. So that's pretty much it as far as administration is concerned. So now it's my pleasure to introduce today's speaker, our very own Professor Cesar Torres. He is an assistant professor in the Computer Science Department, Computer Science and Engineering Department here at UTA, and his presentation is going to be on a very interesting topic, when craft meets engineering, or had they already met. So very intriguing. I myself am looking forward to listening to it. He is also a faculty affiliate of Art and Art History at UTA, in addition to being in the Computer Science and Engineering Department. He serves as the director of the Hybrid ATELIER, which is a creative research makerspace located in the College of Engineering building. And as a researcher, Dr. Torres specializes in human-computer interaction, otherwise known as HCI, synthesizing new media and craft theory into the software and hardware design of tangible user interfaces for supporting creativity. Love to learn more about this. He has received multiple Best Paper awards at top venues within the HCI community. He has a PhD from computer science from UC Berkeley in 2019. So he's been with us for about a year and a half. And a bachelor's in arts, in art practice, and bachelor in science and computer science from Stanford University. So with that, let's all welcome Professor Torres.
All right, thank you, Gautam, for the introduction. It is a pleasure to present today on this fine Friday morning. As was mentioned, the talk is really about kind of these explorations that I've had over these last couple of years, really trying to find what is the middle ground between art and engineering. And just as the one takeaway from this talk, is that they actually have a lot of overlap, but there's definitely these areas that we could definitely build upon to really bring on the next generation of creative technologies. So as a motivating example, I always like to talk about 3D printing. Right now, it's the latest rage in makerspaces, but just a little bit of history. 3D printing is really based off of this one technique called fused position modeling. And so this involves laying down materials, in this case a thermoplastic that you see on the right, in successive layers, leveraging the material's property to fuse with each other. And this was developed back in 1989 by Stratasys. And so if we look on the left, we see a very similar technique. This comes from pottery and ceramics. It's known as the coiling method. And it was developed around the 4th century BC, and it's become the staple of creating 3D forms using clay. So there's a lot of overlap in these two traditions. And so when we try to merge them, we see something like this vase in the middle. It is not necessarily the pinnacle of ceramics knowledge, nor is it the pinnacle of engineering knowledge. There is still a lot of room to build out what is the merger of these two bodies of knowledge. In particular, in this talk, I'm going to be drawing on the fact that craft, and when I talk about craft, it's not necessarily these low-cost, accessible materials. Craft really refers to this method of inquiry that is based on experiential knowledge as opposed to theoretical knowledge. Kind of the knowledge that you get from doing things by hand, and it's very important in constructing tacit skills. things like muscle memory, or even cognitive skills, asked like where to look at and how to recover from error. So despite the fact that there's so much similar construction, there's very little crosstalk between these two disciplines. So there's really this kind of opportunity to combine and what I term hybridize these practices. And a lot of overlaps between scientific and engineering practices. So at the Hybrid Atelier, we're really about blurring the lines between the computer, the human, and the hand, and between digital and physical materials. So let me show you a very typical problem that we look at in the Atelier. So in particular, we've been working with glass. Glass is a very interesting material, both from an engineering perspective, from a construction material, and as well from an art perspective. But we rarely see glass in a makerspace. So we get things like this. So there's a lot of different questions that we ask around these types of situations. What you saw was a glass grinder that was being used to shape glass. And so we have some core human-computer interaction questions. How do we facilitate this conversation between the machine, the human, the tool, and leveraging all the sensor capabilities that we have in our discipline? It's also a very rich data landscape that draws from multiple engineering disciplines, whether it's finding out the activity segmentation algorithm to extract interesting information from these interactions, or designing a new type of glass grinder, whether it's the mechanical or electrical system, or thinking about the material science. How is that carbide spinning bit interacting with the glass, and how can we prevent failures from occurring in this fabrication process? Ultimately, what I'll show you today are a set of design research methods. We are very much interested, how do we combine all these different kind of parameters to create these smart tools? And it begs the question, what is a smart tool? Is it a tool that makes things faster, safer, more usable? Is it a tool that scales and is able to facilitate learning? Or is it about supporting creativity? So the core questions that we look at is, in 20 years, how will we be interacting with these creative technologies? What are the things that we will be able to make, and who will have access to it? And that last question is particularly important because if you look at creative spaces today, it's rare that you'll encounter a screen, a keyboard, or a mouse that can withstand the types of creative activities that occur in these spaces. And part of it is because practically a computer and those interfaces are foreign, but it's also that a lot of the workflows just do not match the type of activities that we see in these spaces. So the Atelier is located in ERB, and it's a lab that's designed to host workshops, conduct user studies, and is a makerspace for working with electronics, wood, ceramics, and polymers, specifically within our research community. So we're closed for now, but this talk is really a sneak peek to see, to show you all the mischief that we've been getting into. The first body of work is focused on designing tools for working with different materials. So these toolkits are ultimately interested in building material literacy. So it's about, if you pick up a new material, are you able to see all the ways you can take it into different directions? It's about supporting open-endedness. So open-endedness is about allowing users to create things that we ourselves, the designers of the toolkits, would have never imagined. And so a really good mental model to think about is the Lego toolkit, right? It's a set of elementary building blocks that really can be taken into different directions to lead to more complex designs. So this first work is some early work from 2016. It's called Proxy Print, and it's at the intersection of metalworking and jewelry making. And this was at a time where in our makerspace, we had just recently acquired a CNC, that's a computer-controlled machine for shaping wire. And so this was a really neat machine, you could specify a design and it would bend a wire into a specific shape. It was a very cool machine, but nobody knew what to make with it. And so here is where craft theory really can change that conversation. Because in order to know what to make with wire, one needs to understand how a wire behaves. And that is exactly this experiential knowledge that we get from making things by hand. So what you see here is a custom 3D printed jig that was printed on a 3D printer that is being used to help a practitioner shape wire into very specific forms. So this particular tool allows us to specify any particular shape and generate these jigs automatically. But it does require very unique adjustments to these geometries to account for work hardening. That is the fact that once you bend a metal, it becomes stronger and more resilient to further bends. And so in the end, what we were able to achieve with this particular system was an ability to create these and fabricate these metal forms that were outside the scope of current CNC wire benders. These wire benders cannot go into such small geometries. But what was particularly unique within the larger research community, well, it was one of the first examples of a 3D printer not printing the final artifact, but printing a tool to help the maker make the final artifact. And so this is a very important human in the loop interaction. It still is balancing fabrication assistance, but leaving some room for creative deviation. Today in the lab, we've been working with shape memory alloys. Shape memory alloys is a wire, just like the one that we saw in the previous slide, except it's known for its very unique properties. And that is, if you apply an electric current or if you heat up the wire, it will return to its pre-trained shape. And so a lot of folks in different communities have been using SMAs to create shape-changing interfaces. So working with SMAs is not necessarily the easiest thing in the world. It's driven by this material science property, where it can undergo different material states depending on the temperature that it's at. So it leverages this property to, when heated, go back to a specific shape. But to train the shape that it goes back to, you actually have to raise the temperature of this particular material above 932 degrees. So we've been using a technique from ceramics where we encase the wire inside of a mold made of silica, and then we are able to kiln fire this to achieve these very new and novel types of trained forms. And this is what essentially enables us to create that vertical bend in that shape-changing paper that you just saw. The other reality is that there's some practical considerations on integrating this type of wire onto paper. So it's changing kind of the landscape of what we consider to be electronic tools. In this case, within the papercraft and electronics community, one common kind of fix is to use Kapton tape to handle the heat stress of putting a hot soldering iron against paper. So Kapton tape is a very interesting material. It was used to shield our space shuttles upon to prevent them from from being damaged on re-entry into the Earth's atmosphere. But today we can use it in these types of applications as well. Another reality is that when working with copper tape, we run into these very tacit and practical concerns. Copper tape is all based, the electrical connection is all based off of adhesion. And so within the papercraft community, we've used tools like bone knives to smooth and adhere tapes and achieve this type of connection that is very useful for electronics. Now, the other reality is that we also have to change our connectors. Here we see on the left a breadboard connector, and here on the right, a very novel paper connector using our old friend, the paperclip. We see these types of grassroots innovations in the DIY communities, and that's one of the things that makes this space so exciting. SMAs are not the only materials that are activated with heat. One branch of our lab explores thermoreactive composites. So this is specifically a combination of materials that use heat to create different states in a system, that use heat to activate them. So all of these works leverage a resistor's ability to generate heat in an electric circuit. Essentially, if we run a current through any conductive material, it will generate heat following this equation that we get from our introductory electronics class. Current times voltage is equal to power. And so we leverage a very common design pattern within circuit design known as the current divider to extend how we can compose heat in these circuits. So we created a tool that allows designers to create custom heat patterns. And so here you'll see this concept artifact that's activating thermochromic colors over time. So that was liquid crystal on a t-shirt. This is thermochromic PLA, a type of thermoplastic that we use in 3D printing. And here's kind of what the workflow for the tool looks like. We're able to segment a design from an environment, and then we have a circuit design tool that leverages the different materials that you're using and allows you to configure how a current divider circuit is going to distribute conductive material across different spaces so that it is still electrically valid, but it gives you very precise power generation rates in different regions of a design. So all of these that you're seeing here on the screen are circuits that are being printed using silver ink. This has been one of the latest innovations using a common inkjet printer. We just fill it with conductive ink. And so then we can take this design and print it, connect it with some copper tape to a power source, and then verify that it is in fact working the way we want it using these reactive materials such as that liquid crystal paper that you just saw. So this allows us to make these little compositions. So let me communicate why heat is such an interesting material and why it's so important to still develop these ways of manipulating heat. Here we see one interaction with a Buddha mala. And so the idea is it's a devotional interface that keeps track of the time that you are engaged in prayer or the number of times that you recite a mantra, similar to how you would use a traditional mala beads. Now, so for all intents and purposes, this is a non-emissive display and a timer. So imagine, opening up your phone, taking out your stopwatch, and timing how long you're praying. It's a very different type of experience that one gets when working using interfaces that engage with different aesthetics, with different materials, and different design histories. And it's not only the thermoreactive material, in this case that watercolor that was changing colors, that can be used to drive these compositions. In one of our most recent works, we've been exploring how conductive yarn and embroidery techniques can be used to both control the different heat regions, but to also create different types of expressions on worn artifacts. So this is very relevant to the community that's looking at wearable technology. So all of these use a material known as liquid crystal. Liquid crystal changes state from red to green to blue, depending on the amount of heat that's generated. You can see these 14 different stitches, all very different, can be used to create these different types of heat expressions. But one of the challenges is also making sure that we are creating electrically valid circuits. And so it's a different type of complexity that we see than in traditional PCBs, in that the amount of traces, we cannot treat a trace with negligible resistance. We have to take those parameters into account. The other reality is that circuit prototyping technologies need to advance to work with these materials. So this is an embroidery hoop that has been retrofitted with these pins that allow us to connect to these conductive yarns and interface with a power supply. This would otherwise not be possible to do, or would be very tedious if we wanted to use something like a breadboard or even attempt to solder those conductive yarns. In another realm, we work on applying advanced computational design algorithms to give new creative parameters to existing materials. In this case, let's take the example of an LED. The LED is a staple of any makerspace, and we see it in all types of introductory workshops. So we can control the expression of light, whether it turns on or off, but that's about it. But within the arts community, there is a long practice of working with light. And so we wanted to create this tool that allows us to generate secondary optic elements for being that allow us to manipulate lights in more nuanced ways. So here's an example of one of the artifacts we created. This is a single LED, but what's unique about this particular hairpin is that we have a custom diffuser that operates at the level of engineered diffusers and is made out of these very maker-friendly materials, silicone and tiny glass beads. And so those glass beads create these very nice refractive patterns and are suspended evenly within a silicone substrate. We also use kind of these mold making techniques to create these different textures, and so it allows these new aesthetics to emerge. Now, this is particularly important if we are thinking about putting technologies on the body. There's a lot of issues with adoption, whether or not folks feel like a cyborg wearing all the what is the tech aesthetic on their body, versus looking at these new aesthetics to try to change those perceptions and really address adoption within different communities, especially those around accessibility. Now, the tool that we developed in illumination aesthetics is also able to lay out LEDs in many different ways that go beyond the grid or the strip. In this particular case, we have the cityscape that has about 32 LEDs. It uses a custom reflector underneath to direct lights in different ways. And one of the reasons that we really liked this particular artifact is that it was one of the first instances where we could touch light. This is silicone. Silicone is this rubbery substance, and so it has a very playful aesthetic. And so we're really we kind of went with this. We loved how silicone was flexible and soft, and it wasn't something that we normally associate with electronics. And lately, it's been one of the driving materials in fields such as soft robotics. So here's version 2 of that, of extending that idea. But instead of a static diffuser, we have a silicone bladder. So this silicone bladder essentially is a vessel that allows us to inject air and create these balloon inflations. And in particular, how inflated it is changes how the light interacts inside of it. So you kind of see this more blending of the different rainbow lights inside when it's fully inflated, and you see a little bit more definition in that rainbow when it's not. But from an interaction standpoint, it gives us this playful resistance. It kind of resists you clicking on this proverbial button. And this has very large it's very relevant to augmented reality applications. So imagine being able to play your favorite video game, and you have a controller that can take the full force of your punches and your strength. This is something that we don't really see with computer technologies, and one of these kind of opportunities of designing these soft interfaces that can take the punches. And this is also where craft really shine through. Silicone is amazing, but it has these very practical drawbacks. It's very time consuming, and that bladder that you saw took about a day to make. And for those of you who have ever worked with silicone or have visited a polymer fabrication lab that does, you'll know that silicone is incredibly messy. There's no way to not make the entire lab sticky. And you have a very limited amount of time to work with it. It involves mixing two reagents, an A and B reagent, and allowing those reagents to cure. And you have about, depending on the silicone that you're using, about 15 to 20 minutes to work with it. And the whole process of making these molds is a huge time sink. So even within soft robotics communities, we see entire papers devoted on making one specific end effector that takes about 3 days to fabricate. So we took this process and we were able to reduce, for example, in making that bladder, it takes normally 6 hours to make across 2 days. We were able to reduce that fabrication time down to 5 minutes. And the chief innovation was really inspired by a craft technique, the lost wax mold making technique. So in lost wax mold making, what we have is a wax form that we then put in a mold material. So in this case, it's typically some sort of concrete. The wax is then melted out of this mold and replaced by a casting material, in this case metal. The metal is then removed and sacrificed from the mold, and then some post-processing occurs to get that final metal form. What we ended up doing was using this material that has recently been converted into a 3D printable filament. It's known as polyvinyl acetate. And one of its most unique properties is that it can be dissolved with water. So we put this PVA material inside a silicone mold. We then inject water into that composition, dissolve out the PVA, and then inject air. So that's the basis behind our fabrication technique. And we support it using a variety of design tools, of automatic geometric generation, and to generate all the different parts that are needed in order to generate arbitrary forms. So here's what that process looks like. Right now, what I have in that mold is one layer of silicone. I'm putting that polyvinyl acetate in the shape of a octopus into that mold and covering it with a sealing layer of silicone. We speed cure this so that drastically reduces the final processing time. And within those 15 minutes, we can then inject water into this structure, dissolve out that polyvinyl acetate, and we can do little speed ups like agitating the mixture or putting it inside of an incubator to heat up the dissolution. And in the end, we can then fill that with air. So these inflatable structures have some very interesting applications in the space of worn technology. For one, they're skin safe. But one of the things, if you think about the technologies that you wear on your body, is that our ability to create motion to act upon the body, or what we call actuate the environment, is very narrow. And what I mean by that is typically we use motors, some sort of electromagnetism or resistance to create these physical changes in the environment. And what these all share in common is that they're incredibly power hungry actuation methods. But in the case of pneumatics is really interesting because we can continuously inject air. This particular system remains stable. We can just close a valve. We don't have to be continuously pouring current into this particular mechanism. And on top of that, we can create emotive forces on the body that far exceed that vibrating motor in your phone or that heat strip in your portable heated coat, for example. So here's an overview of this system that we have been creating in our lab to better to be able to compose different types of haptic sensations using pneumatic compression. So this bladder is held against the body using a Velcro or some fabric. Let me bring that back again. And this is fed through a decoupled pneumatic controller where we can both inject air through a pump or suck air out of the system through a vacuum, as well as sense pressure readings in the overall system. So this allows us to create different gestures on the body. But one of the realities is that even with these silicone bladders, it's incredibly difficult to interface to different types of materials. So here are some kind of innovations on adding, for example, hard materials to this bladder. In this case, these plastic tacks that can create this almost painful sensation when this bladder is put up against the body. So here's an example of one of these bladders that has been fully embedded into the clothing. It's, in this case, this is a stress glove interaction. And what we can do is detect squeeze gestures. So we can dynamically inflate that bladder and walk somebody through some stress relieving technique. Or maybe it's the basis for haptics for virtual reality, such as a fighter pilot game that allows you to engage with your controller by squeezing this interface. What's next in the event horizon? We have been busy making some kombucha leather. So this is a flexible biomaterial. It's leather-like in texture and strength, and has wonderful opportunities to bridge bioengineering, paper making, and leatherworking, especially here in Texas. So emerging materials, it's a very fertile research area, a lot of innovation to build these respective practices. But at the same time, developing a practice is more than just a toolkit. And so in another body of work, we look at building tacit knowledge repositories. So I'm sure many of you have felt those frustrations from following those step-by-step tutorials that don't really capture all the little nuances and kind of differences between what you have and what they have. Things like a missing ingredient or a deviation, like I forgot to do a step, what should I do to recover? There's environmental conditions. Maybe it's a little warmer in the environment in which this tutorial was made, or maybe there's just different skill in being able to manipulate different materials. And I think we've all experienced these difficulties of transferring what is tacit knowledge. These are bits of information that just resist being recorded or documented using traditional media, such as the missing bits of information from a cooking recipe, from a bioprotocol, or that API that we can only learn through trial and error and practice. So I've been looking at ways of capturing and storing and transferring tacit knowledge. And this is work that I've been doing with my PhD students, Akib and Triyoshi, and with one of our newest collaborators in the UTA glass department. So this line of work tries to understand fundamentally two questions. How can we better document these hard to observe bits of information that often go missing in tutorials or instructional material? And how can we leverage more of the body? Now this might not, this connection might not be altogether there, but I want you to think, especially for the computer scientists in the room, the way that we model the human mind is a lot of how we think about the actual computer. We have a CPU, just as the mind has our cognitive processor. And so we always want to try to minimize the amount of load on our CPU, on our mind. And so one way that we do this is by offloading it to hardware. We do hardware accelerators, and it does these hardware accelerators make use of the fact that there's these repetitive operations that we don't need to burden the CPU with. Instead, we can offload it to a different subprocess. In a very similar way, that's how our body works. We have muscle memory. These are structures, cognitive structures that allow us to offload things like breathing, walking, or manipulating a tool to different sectors of our brain rather than to our attention, to our the cognitive processor within our brain. So to that extent, designing devices that interface with more of the body is a way of incorporating this type of acceleration into our bodies, such as how you might see a foot pedal when using a sewing machine. One project that we've been looking at is the emotional regulation of a person engaged in programming. So I'm sure for many of you, programming looks like this. But for some, especially those new to programming, it feels like this. Through practice, there's these highs and lows of engaging with programming that for some might mean dropping out of their programming course or engaging in a lifelong pursuit of a programming practice. So I want to talk about one study that we've done. In particular, we looked at 17 participants with varying degrees of programming experience, and we recorded their actions for about 40 minutes while they were wearing a biosignal wristband. So what this wristband gives us is two types of sensor feeds. One, phasic electrodermal activity, and the other, heart rate. And so these have been used in effective computing to roughly correlate to event-driven stressors, as well as the valence, or roughly how happy or sad a person is. And so from our study, we were able to collect these data feeds across all 17 participants. So imagine viewing that data, specifically in that waveform, side by side. This is a reality that many social scientists face, and it's one of the main reasons that sensor-based ethnography has had so little traction in the field. It's very difficult to extract insights from the data being represented as traditional line plots. So we created this visualization method that identifies the most unique subsequence of behaviors across the entire data set in order to identify what are some of the unique behaviors that are occurring. And this uses a machine learning, unsupervised machine learning technique known as activity codebooks. And this allows us to plot all the participant data on a single screen and visually identify some patterns. So what we've done is we've segmented these two groups based on the frequency of their code words, which looks something like this. And visually we can see there's some difference in pattern between group A and group B. But let's go into one of those in detail. So this is Rachel. Rachel is part of the group B. And I want to first, let me walk through how to read this particular graph. The background of these respective areas, the yellow, green, blue, and green, correspond to the specific programming problem that the student was on. So in this case, yellow was a print loop statement, so print 10 numbers out in line. Green was a dynamic programming task, and blue was a string comprehension task. What we see, I want folks to focus on the heart rate. What we see is this phenomena where the heart rate, the peaks in the heart rate, are capped by the specific bounds of a problem. So for example, here in this very simple print loop statement, we see a very slight rise in heart rate. Here, we see Rachel is reading this particular problem, and she decides it's too much for her to go through. We kind of see this in the typing activity. Here it's just reading, and here she tries something and decides, better not, let me move on to the next problem. Here she gets a little bit more traction. You see a lot more typing ability, typing activity, and if we look at these areas where we have compilation events, these are marked by the orange bands, we see that roughly the heart rate is kind of bounded by these regions, which is a very interesting phenomena. And they're also bounded by the actual problem itself. So what we can see here is that Rachel can withstand a couple of fluctuations in her heart rate before she moves on to different problems. Now let's take a look at somebody from group A. So this is Renee, and as you can see here, she also did not struggle with the first task, the print loop statement, but she decided to go all in on this second problem. See those fluctuations, see how many compilation events. This is a very different type of activity. And it shows us a little bit more about how emotion is being regulated during these programming activities. So what's the difference between Renee and Rachel? Rachel is a third-year mechanical engineering student. Renee is a graduate student in computer science with more than 20 years of industry experience in back-end development. So despite the range of expertise, both Renee and Rachel approach this screen problem with the same strategy. They had practically equivalent solutions, but in terms of how resilient Renee was to these failures, she was able to have a much better programming experience, whereas Rachel was not happy with her performance. And so this really indicates that heart rate might be a really good indicator of resiliency, and something that we could potentially incorporate into how we teach computer science. How might we develop this resiliency so that we train programmers that are able to deal with these adversities that they face in the field, and be able to find joy and value from going through all these, through the highs and lows of that emotional roller coaster that is programming. So we've been trying to turn this into practice. This is kind of a teaser to one of our latest projects. It is inspired by a debugging strategy known as rubber duck debugging, where a programmer talks to their inanimate rubber duck through all the different lines of code. And it's based off of a really common research method within user studies, the think out loud. If you think out loud what your mind is processing, it's easier to understand the different biases that you might be introducing, rather than just keeping it all in your head. So we've been designing these tangible avatars that allow you to compile your code through different touch interactions, but at the same time we display the data from a heart rate sensor in the lights that are being projected through the duck, in a way to create this almost ambient data mirror, so folks are more conscious of their respective behaviors when they are programming. We're currently running a user study on this, so stay tuned as we learn a little bit more of what presenting these emotional data signals does to the experience of programming. Of course, emotion is just one component of tacit knowledge. A large gap is around physical skills, such as pottery throwing. So when the pandemic closed down all in-person instruction here on campus, one of the areas that were specifically affected were the art practices, as well as any other type of instruction that required the use of labs or facilities. And that it really points to this large issue around how do we communicate these types of tacit knowledges in this more distance learning type of situation. And these are questions like, what pressure should I add? In what direction should I apply that pressure? How long should I apply that pressure? And what should it feel like? So this is one of our current studies occurring here in January. And our work is really trying to look at different types of sensors. So in this case, electromyography, which gives us information about pressure being exerted by different muscles in the hand. And so our main goal is trying to rethink how we present in tutorials, in this case, a YouTube video, to match with the realities of, you know, the hands are dirty, they cannot interact with that video. The video is out of sync with what types of challenges that they're facing, and they have no way of, in a lot of these situations, these videos rarely go over the error or failure conditions that one often encounters. So we are looking at bridging these particular gaps using this sensor-based ethnography methods. I'll conclude by talking about this last project, which has been looking at one of the most underappreciated conveyors of tacit information, and that is sound. A creative space is filled with a medley of sounds that inherently encode valuable information. And over time, it's internalized by practitioners as feedback mechanisms of appropriate use, ways to adjust behavior, guide creativity, or often to diagnose when something is not working. So we've been building this smart tool, which I showed you in the start of this presentation, in this case, a smart glass grinder that can survive in a glass, where this particular system could survive in a glass shop. So we particularly built this audio logging device, all wireless, all based off of the Internet of Things. And our main goal in building the system was to support data collection. Now, data collection is one of those tacit skills that we don't necessarily give as much value to when we are designing our respective machine learning models. But really, in order for us to build robust and repairable deep learning models, we have to think about data collection. So our particular data collection method is nothing special. Here we have a momentary button that is allowing us to log audio data for grinding events. In this case, we're annotating, is the person grinding or not grinding? But in the back end, what we are able to do is create these bespoke data sets. So while we recorded a particular data event about a person grinding, that may be useful for another type of model. But being able to organize and collect this data and make it usable for machine learning is a very difficult process. And so we've automated elements of this where we can bring different recording records and place them as positive and negative examples of a data set, or at this point, binary classification. And then we can send these respective models to be trained. In this case, we use a ResNet 101 deep learning model to see if we can segment different types of activity in the workshop. So for example, I could have a bunch of records of novices using the glass grinder and a bunch of records of experts using the glass grinder. And that is very useful for constructing a model of expertise. Could we quantify a person's skill just simply by the interactions they have with the machine? At the same time, because this is all on a connected platform, we can design specific interventions. For example, in this case, illuminating a side-worn light piece on safety glasses to indicate to a user improper use of the grinder, or to indicate to a shop manager whether somebody might need extra assistance. In our event horizon, we've been working with the UTA glass department in bringing some of these interfaces to the hot glass shop. For example, you can see the incredible amount of tacit knowledge involved in communicating the rhythm and cadence of a rod during the act of hot glass blowing. So these are some of the exciting projects that we that happen in our lab. And ultimately, our goal is to build these repositories of tacit knowledge and figure out new ways of communicating them across distances, and in the design of smart tools to support creative thinking and learning. So in the end, craft and engineering have had a very long history together, but there's definitely opportunities to grow these connections. I've shown these, and I'm always open to new collaborations around material toolkits. How might we democratize a technique or method that is inherent to your work? Or around tacit knowledge, how can we mine and document that hidden information that always escapes written record? So I want to conclude with a big thank you to my lab, the incredible set of both graduate and undergraduate students across the engineering department and in the art and art history department. And with that, I'll open the talk for any questions. Thank you.
Thank you, Cesar. Great talk. I learned a lot myself. Pretty fascinating, you know, the kind of different domains that your work is really focusing on. You know? So I think we would like to open up the floor for questions from the audience. So folks, if you have any questions for Dr. Torres, please make sure you write them in the chat box and I will read them out. While that's happening, you know, I had a couple of questions for you, Cesar. You know, this is something which is intriguing to me itself. I guess, what kind of background do you need for a student to, let's say, work with you? I mean, it's a little unconventional, the kind of work you're doing, very fascinating. It's cross-disciplinary. I mean, just wondering, you know, how would you get somebody to work with you and get productive soon? I mean, do they have to be a material scientist in addition to being a computer scientist? Do they have to be an art student, or do they have to be a little bit of everything? So,
right. So that's a great question, and one of my favorite things of running the atelier. What I end up doing is I recruit students from all different types of background. And what I'm particularly looking for are students that have applied their knowledge into actually making different things.
Okay.
And so to the extent of like, how do they make sense of all this type of activity that's occurring in the lab? It's really by the simple fact that they interact with each other. So, you know, I have a bioengineering student that was working with the kombucha leather, but then mechanical engineering student tells them about, hey, you could control the temperature using a PID controller. And so there we get that beginning of that dissemination of knowledge across two people. And really, the more time that you spend in the atelier, the more time that you start picking up the little skills, the little bits of knowledge that kind of constitute all of engineering, but also because it's a design lab, it really engages with humanistic thought. So I really pride myself in the kind of discussions around ethics that we have in the lab. And it's one of my favorite reasons for having just so many different people to just grow that knowledge over time.
Okay, great. So I'm just reading, we have a question from the audience. Alex has a question. Is heart rate the only metric you're analyzing to measure resiliency? And that's an interesting question because, you know, the human beings are complex and heart rate is, you know, kind of simplistic, right? So.
Absolutely. So for the purpose of the talk, I kind of give you only a sneak peek. We actually looked at a lot of different types of signals. So let me just backtrack a little. So in the case of emotion, we looked at, let me just navigate to this. Okay, so you'll notice on top we have another chromatogram that I didn't cover. That one specifically looks at activity logs with a Jupyter notebook. So it's taking into account when are people compiling? Did they get, what types of error messages did they get? What types of IDE interactions are they doing? Like, are they adding cells, removing cells? So that gives us a really good indication of programming practice. So for example, there was folks that only worked in a single cell. And that was because they were trained traditionally as in a traditional IDE, where you only have one page, and that's where you kind of work in. Versus folks from mechanical engineering, which traditionally learn programming through a language like MATLAB, are much more familiar with this type of interaction. And those are things that we could piece from the interaction process chromatogram. Now, in the case of emotion, we did have the full EDA, so we had both phasic as well as oh, I'm blanking on the word. A measure of electrodermal activity that doesn't that indicates more longer-term trends in emotion. On top of that, we had a retrospective think out loud. So this is a technique where you ask the user to look back at their session, so to go back through the video of their programming session and to annotate the video with how they were feeling. So we'll go to different areas of the video, and they will give us a Likert scale response that gives us a little better idea of the emotion. And then the last bit is that we had questionnaires that kind of evaluated the end session. So that's kind of the yellow annotation that you see on the left y-axis of these chromatograms. If the session was reported above, like an above average experience, it's annotated in yellow. And so you can see some good indications between group A and B. But the kind of larger point and kind of issue with all of these types of methods is the balance between statistical power versus qualitative analysis. In ethnography, you typically only look at 4 to 5 people. And so this was a very strange ethnography in that we had 20 people, or about 20 people participate, and we could still make sense of some of that data. We eventually would love to incorporate more types of biosignals, and that's one of the things that we're doing in our latest study.
With regard to the sensors that are monitoring human performance, what kind of challenges do you see when it comes to deploying them in sort of real world situations? I mean, will there be resistance to this kind of monitoring, privacy issues, anything that you have started thinking about, or you think that it's a problem somebody else should worry about?
Right. No, it definitely has large ethical implications. So, for example, I talked about heart rate as a measure of resiliency. That could definitely be used by recruiters to gauge programming abilities really quickly. And it really biases, for example, those that have that process emotion differently. For example, certain types of mental health disorders. And so it does bring those, there is that potential for it to be used in that way. One of the ways that we want to kind of get around that is typically when we have, let's say, a traditional scientific experiment, we have two different conditions that we bring into the equation. So for example, when in other studies that look at programming abilities, they look at novices versus experts. What's nice about this technique is that it's unsupervised. So we don't know if group A is full of experts or group B is full of experts. And one of the things that we saw in this particular study that kind of shows that is the folks that had the best experience were actually those that were trained in the Jupyter Notebook or that came from a MATLAB originating programming background. And so that just means that when we for example, teach computer science, we have to pay attention to the backgrounds of specifically what IDEs these students are coming from in order to tailor content to better fit their understanding. So again, it's just pointing out these little, it's deconstructing that whole master apprentice notion that we know what's good and what's bad, and being able to detect all the different programming styles that are out there so that we generate our theory from ground up, as opposed to keeping on percolating the existing theories and models that may have changed over time.
Great, thank you very much. Yeah, it's been a fascinating conversation, but we have reached the end of the hour, so I want to respect everybody's time. So let us take the moment to thank Dr. Torres for this fascinating discussion, and enjoyed having everybody attend. We will continue the series with other great speakers later on, but for today, let's thank Dr. Torres again. Thanks, everyone. Bye-bye.
Thank you, everybody.